Let's get started. It's my great pleasure to introduce our first invited speaker, Moritz Hardt. He is a professor in the Department of Electrical Engineering and Computer Sciences at UC Berkeley. He's one of the co-founders of the FAT-ML workshop, which is Fairness, Accountability, and Transparency in Machine Learning, and has done a lot of wonderful work on societal impact of machine learning on fairness, validity, and many other topics. He is a recipient of many awards, including the Best Paper Award at ICML and iClear. And take the stage.
All right, thank you very much for having me. Thanks so much to Daniel and Alina for organizing this wonderful conference. It's an honor to be here and speak here. Even though, for the last 2 months, I've been basically getting trolled on the internet about the size of these, headshots on the webpage, okay? So I'm glad that's over now, okay? So Emma and I are greatly relieved that, this website will be retired. So anyway, so the main thesis that I want to kind of put pressure on and in this talk and kind of explore is what governs overfitting in the machine learning community are psychological and sociotechnical patterns that are inadequately captured from a purely statistical perspective. And I'll try to unpack this thesis throughout the talk and tell you what I think we can learn from it. And this is both a retrospective on a field and also maybe suggesting a bit of a reframing going forward, okay? So let me give you a bird's eye view of machine learning, and this is obviously oversimplified, but there is a community of very talented people with peculiar interests, and they really enjoy working on certain benchmark data sets like CIFAR10 and IMAGENET or other benchmarks, MNIST. These are some popular vision benchmarks. And at a very high level, what the community is doing is they're coming up with models that they trained on these data sets, and they're evaluating them on test data. So they're querying the test data to see how well the model is doing. And how well the model is doing is usually captured by some loss function. For this talk, you can just think of the error, like the 0-1 classification error, just how many prediction mistakes you make. And this goes on and on. Okay, so based on the loss that they observe, they come up with new models, tweak their existing ones, propose new architectures, and this goes on and on and on. And this is at a very high level how the machine learning community operates. Okay, and the thing that makes this all work scientifically is the holdout method. And so just as a recap, most of you know this, the holdout method works like this. You set aside holdout data of size n that you draw from some population, or imagine it's drawn from some population, and we'll assume it's drawn IID from a population P, even though most of the results I'm going to talk about could work with different assumptions too. And you use the empirical risk on your holdout set, which I'll denote by R sub S of F, which is just the average loss over the test data, over your holdout set, of your loss function. Again, this could be 0-1 loss. This is what I call the empirical risk, and you use the empirical risk as an estimate of the thing that you're actually interested in, which is the population risk, or simply risk, which is the performance of your model on the underlying classifier. Okay, so you use your sample estimate, the empirical risk, or just the empirical average, to estimate the quantity you actually care about, the population risk. Okay, so this is familiar to most of you. If you have questions about this, stop me now, because I'll assume these notions are familiar to you. And the fundamental quantity that relates this sample estimate and the population quantity is what I call generalization error. For this talk, I'll just say error because there will be no confusion. I won't talk about optimization error or other things. Errors will always be this kind of error. It's the difference between the risk and the empirical risk. And this tells you how much the empirical risk underestimates the true risk. Okay? So if this quantity is large, it means that your sample estimate overestimates the quality of your model or underestimates the error of your model relative to the actual population parameter. Does that make sense? All right, a lot of people nodding, so let's take that as a consensus yes. And so keep these notions in mind. This is the only technical slide I have, or will maybe be the most technical slide. Question, Lev.
You don't have absolute values around there, so technically it could be negative.
It could be negative, yeah, and we'll typically bound this in absolute value, but so if you want to throw the absolute values in there, sure, yeah, that's right. And so what are the basic guarantees of the holdout method? if you fix k models or k functions independently of the data, the holdout method will give you maximum error of root log k over n. Okay, so 1 over root n is just the standard deviation of the sample estimate, the empirical risk, and the root log k you get because you take a union bound over k things. Okay, and so you get an extra root log k. This is just Hufting's bound and union bound combined. Okay, but so you might look at this and be like, okay, this is great. In principle, you can evaluate exponentially many functions on your data and still get non-trivial error bounds. Okay, so this seems like a good bound that could get you very far. But there's a big catch that people realized or recognized 4 or 5 years ago, which is that there's a closed feedback loop between the analyst and the data. Okay, and so what this means is machine learning is adaptive. Models incorporate previous feedback, previous insights from the test data. And this is the whole point, right? The whole point why you evaluate against the test set is so that you learn something about your model and you can improve the model, okay? So machine learning in the way that I depicted it on the first slide proceeds in this closed feedback loop kind of way by which the more you probe the test set, the more you query the test set, the more your model can incorporate information from the test set. And this is what came to be known as adaptive or adaptive data analysis. And so the issue here is that once you redo the analysis of the holdout method in the adaptive case, you get much worse bounds, okay? So for k adaptively chosen models, when you're allowed to incorporate previous feedback, holdout estimates are only accurate up to a maximum error of root k over n. And moreover, this is tight. So you can find a very simple strategy that just makes k queries and gives you a deviation of root k over n, okay? So contrast this to root log k over n. So it seems like we lost sort of, it's a kind of an exponential blow up in k. In particular, if this bound attained, you could only make like a linear number of queries to your test data before you lose all validity and you can throw away your test data and collect a new one, okay? So this is a pretty bad bound. And we looked at this and we were a little bit alarmed by it and worked hard on this and came up with a different and alternative holdout mechanism that gives you slightly better error bound. And so this is from work by Dwork, Feldman, myself, Pitassi, Rangel, and Roth, later improved by Basili, Nissim, Smith, Stemmer, Stank, and Ullman. And this is an alternative mechanism. It's not just the empirical risk. It uses noise addition in conjunction with the empirical risk to improve this error bound from root k over n to k to the 1/4 over n, okay? So that's like a quadratic improvement. It means you can do like a quadratic number of things before you burn through your data. Okay, so there's an improved bound. It's probably tight. There's now evidence that it's tight. But I hear you say, but still, this is like still kind of pessimistic, right? You only can do like about a quadratic number of things before you lose your data. Okay, so you might say, if this actually attained in practice, this bound, you would very quickly still burn through your holdout data, okay? And so this raises the question if we're doomed, right? There are all these bounds like root k over n, k to the 1/4 over root n, and I was worried back then if we're simply doomed. If the machine learning community is simply putting too much pressure on this holdout paradigm and testing their data too often, reusing the data sets too often. And so in 2015, when we started working on this, I was a little bit alarmed. I was a little bit worried. I thought that maybe this is not going to be sort of a method or a methodology that's robust enough to sustain progress. Okay? But then, let me tell you about 2015, just in case there are some students here who don't remember who remembers 2015? All right, some students in the room, didn't even do computer science back then. So, this was a great year. 2015 was amazing. ImageNet was the thing. It was like the greatest frontier. If you like cracked the number one, place on ImageNet, you popped the bottle of champagne and you partied and it was great. And, deep learning was hella lit. I mean, you could, make a ton of cash with it and you just had to know how to import TensorFlow and, set the random seed. This is like from the 90s. Okay. Anyway, and Kaggle was a cool startup. Okay, so there was a really exciting startup back then called Kaggle, which organized machine learning benchmarks that proceeded in the same manner. You had like a holdout set, you tweaked, or you tried to compete on that holdout set for the number one place, and you can make money and fame as a data scientist. Okay, so 2015 was an amazing year. But it had me worried a little bit. And so now it's 2019, 4 years passed, we're getting all a little bit older, we learned something, okay? And there's actually been recent, insight into this progress, recent meta-analyses that I found quite surprising. And so in particular, people looked at CIFAR10 and ImageNet, and this is work by Recht, Roloff, Schmidt, and Shankar at UC Berkeley. And what they did is they recreated in sort of painstaking detail test sets, new test sets for CIFAR10 and ImageNet. So they followed the exact creation process of the original CIFAR10 and ImageNet test sets to recreate what is plausibly a new test set for these benchmarks, or two new test sets respectively. So they carefully looked at the original data generating process and they tried to recreate it as accurately as they could. And then they took all models that had been proposed over the years and threw them at the new test set, okay, to see what happens. And what they found is that the model ranking was preserved, okay? So if you rank the models on the original test set and you rank them on the new test set, you get more or less the same ranking, okay? So whatever was the best model on the old test set is also the best model on the new test set. And the more you improved on the old test set, the more you would have improved on the new test set. So that's kind of amazing, and you can put that in a plot where you have the original test accuracy on the x-axis, the new test accuracy on the y-axis. The dashed line is just x equal to y, that's no change. And so the models all drop. They all get a little bit worse. This could be distribution shift or like an systematic bias in the data generating process. They all drop. But importantly, and this is what I want to draw your attention to, the slope of this line, first of all, there is a linear fit through these data points. These are all these models, like every blue dot is like a model. And there is a perfect sort of linear fit through these models. And moreover, this linear fit has like a good positive slope, which basically says the more you improve on the old test set, the more you improve on the new test set. And this is kind of surprising, right? In particular, it makes kind of a case against adaptive overfitting, and let me explain to you why. So it means that the performance of the newer models drops less on the new test data, even though they had more time to adapt, right? So you look at these newer models, which had, you know, so many years, 4 years to adapt, instead of the older models, which had only a year to adapt. And the newer models overfit less in some sense, right? So you see that there's this line actually tilts a little bit upwards, so the difference is larger at the lower end than at the higher end. But in particular, if you extrapolate this linear fit, what you get is that if you continue hacking away at ImageNet, eventually you also solve the new test set. Okay, so if you just keep going, you keep improving accuracy on the old test set, you also improve on the new test set. That's quite remarkable. So we wanted to see if this holds up, and we looked at all of Kaggle, as a matter of fact. This is new work with Friedrich Keil, Miller, Recht, Roloff, Schmidt, and Shankar. And we did a meta-analysis of about 287 Kaggle competitions. This is, Kaggle has a metadata data set, so to say, where they have details about all of their competitions, and we work from that. It's a little bit messy. And there's, you know, minimal evidence, I would say, of systematic overfitting due to adaptivity. There are some notable outliers. There's some competitions where terrible things happened, where things went completely wrong, and you can see like a lot of differences between sort of the public ranking in the competition and the final ranking. But by and large, we see very little evidence of adaptive overfitting, even in the vast majority of Kaggle competitions. And you know, even MNIST, for crying out loud, okay? So people also did this on MNIST. There's a new paper by Yadav and Boutou, which has a great title called The COLT Case, The Lost MNIST Digits, where apparently somebody found MNIST digits. I forgot what the story was, in like a drawer or like on the streets or something, but there were like suddenly a lot more MNIST digits than people had, you know, sort of previously assumed. Somebody discovered these, you know, lost MNIST digits and just used them as a new test set, okay? And you get the same picture. So even like, and you know, don't try to read these X and Y axes because they're kind of swapped from what we previously did, but it's the same story, linear fit, and the more you improved on the old test set, the more you improved on the new test set. So even MNIST, this terrible benchmark that we've been using for 2 decades and like seem to be completely overfit against, right? Like, you know, people have like 99.8% accuracy or whatever on this benchmark. Even there, you get the same monotonicity when you get a new test set. So that is somewhat surprising. So what I want to talk about in this talk is this question of what makes data live so long? Why do we see this longevity in these machine learning benchmarks? Why can we tweak against MNIST for decades and still get progress even when we resample the data? And in particular, I want to tell you about 3 unexpected forces against overfitting, or 3 forces that promote longevity of data, if you will. And they're not necessarily where you thought they were, okay? So in particular, I'm going to talk about community dynamics, about the mind of the analyst, what goes on inside the analyst, and problem artifacts, how seemingly subtle and often ignored aspects of the data have an important effect on these outcomes. Let me start with community dynamics. And this goes back to work from 4 or 5 years ago with Avram Blum. One thing we kind of postulated in this work is what we call the ladder principle, okay? And the ladder principle says that analysts mostly care if they improved on the previous best, and you ignore models that didn't improve, okay? So when you hack away at these benchmarks and you're trying to win a Kaggle competition, you mostly care if you beat the number one, okay? You don't care so much if you come in sort of in the middle. In that case, you kind of ignore the numerical score of your model and just sort of try something else, okay? This is in some sense a postulate about how the community operates in such situations. And you can turn this into a definition, into a formalism that we call leaderboard error, where, going back to this picture of the community that queries the test data and gets back an estimate, instead of giving them an accurate estimate about each of the model's losses, what you do is you just try to maintain the best model, okay? So your goal with leaderboard error is to maintain an estimate, R sub t, that tells you what the loss of the best model is up to point t, okay? So you imagine this proceeds in steps and rounds, whatever. T is the number of steps you've seen so far, the number of models you've seen so far, and you just want to know what is the best model, the loss of the best model I've seen so far, okay? You can put that in a definition that we call leaderboard error. So the leaderboard error of a bunch of estimates, R1 through Rk, is just the maximum of all steps in your competition, 1 through k. And at each step, t, you look at the difference between rt, r sub t, the estimate that you have currently, and the best loss you've seen so far. So the minimum of all previous steps of the risk of the model at that step, okay? So you're simply writing out what it means for rt to track the loss of the best model seen so far. That make sense? I'll give you a moment to parse this and let me know if this definition doesn't make sense. So instead of telling people what is the loss of your model, you tell them whether they improved or not, okay? In other words, whether they beat the number one or not and what the score of the best one is so far. Let me operationalize this definition with an algorithm that's very natural. We call this the ladder algorithm. And all you need to understand for the ladder algorithm is this picture. There is a worst possible loss. Let's call that R0. And in the case of classification error, that's just 1. You can never have error worse than 1. And there's a current best loss, R sub t minus 1. And you say, hey, I'm going to give you a target that you have to beat, R sub t minus 1 minus epsilon. And if you beat that target, R sub t minus 1 minus epsilon, if you improve on the previous best by a significant amount epsilon, I'm going to say you're the new number one, okay? And you keep doing that until you hit the bottom or not, right? Until people stop improving, okay? So you just keep going as far as you can, and the best possible loss is 0, okay? There's a bounded loss function between 0 and 1, so the scale goes from 1 to 0. You can never go below 0, and whenever you update your loss, you go down by at least epsilon. So the algorithm works like this. You start from R sub 0 equal to 1. And for k steps, what you do is just the following. You receive a model f sub t at step t, and you look at whether the empirical risk of your model is less than the previous best minus epsilon. If it is, you update your estimate to the empirical risk of your current model, the one that you just saw. And if it's not, you tell the analyst, I'm sorry, you didn't improve, and you just take the previous estimate, okay? So basically, you give the analyst a target. They have to get below the previous best by an epsilon. And if they do, you update your score, and you say you're now the number one. And if not, you don't update your score, and which signals that they didn't improve, okay? This is just the ladder mechanism. The only thing you have to remember is this picture, okay? There's actually something really intriguing that happens when you look at the best possible leaderboard error that you can achieve. There's a lower bound of root log k over n. That's just the non-adaptive bound. You can't get better than that because even in the non-adaptive setting, you would pay that much. And this upper bound, the algorithm that I just described, the ladder algorithm, gets you log k over n to the 1/3. So it looks kind of right. It has that log k thing going on, but the exponent is wrong, okay? So this is cold. What does like a half and a third scream at you? Come on. Where are the bandits? Okay, so somehow I kept looking at this and I was like, one of these COLT people can just like be like, oh, this is like the such and such bandit problem with like these kinds of arms, and this is what you should do, and to close this upper and lower bound. And so I waited for a while to like, for the people over there to like tell me how this works, and they didn't. So I came up with like a really sloppy new upper bound of like log K over n to the 2/5. I mean, come on, you gotta be kidding me. And the hardest part of this paper, seriously, was convincing me that 2/5 is actually bigger than 1/3. I'm still not completely sure, to be honest. Like every once in a while I have like a nightmare where I wake up and I think it's like actually smaller and you know, I did it all wrong. But I think it's somewhere here. It's somewhere between 1/2 and 1/3. And so maybe more interestingly in that paper I also give evidence that this is probably the tight answer. Okay, so I have a reduction to a different problem where we believe that you can't improve the upper bound. And so there's evidence that this is actually the tight answer, somewhat surprisingly. So you get an exponent that's strictly between 1/2 and 1/3 for one of these like online looking problems. But the tight bound like provably is still out there somewhere, and I don't know how to get it. So this is probably a difficult question at this point. All right, cool. So one thing I find fascinating about the ladder algorithm that's always like intrigued me about it is that there are two ways of thinking about it. One is as an algorithmic intervention, and one is as a natural algorithm, in the sense of like Bernard Chazelle. You remember Bernard Chazelle's natural algorithms. You know, who remembers natural algorithms from 2009? It's like this 120-page paper, it's like about bird flocking, and like, it's a beautiful thing. And so basically a natural algorithm, according to Bernard Chazelle, is something that nature or society or some you know, community implements on its own without an active intervention. Okay, and I'd say this algorithm is actually kind of both, okay? So I think of it as an intervention when you design a competition and you really want to make sure that you're not overfitting and people don't abuse the data set. You can enforce this as a limited feedback mechanism in a competition. That's been done, and you know, it's something that you know, probably helps. But you also can think of it as a natural mechanism, as sort of a postulate about the community, that the community is really only impressed when you improve significantly on the previous best. And we tend to ignore models that didn't improve on the previous best. Okay? Sure thing. You get R sub t, but you kind of know when you improved and when you didn't, right? Because you just get the score, but you can assume the analyst knows the previous model. So you can imagine the whole transcript of models and answers is public, and you can reconstruct whatever you want from it.
What if your minimal possible error is not 0?
What do you mean not 0?
Well, you said
Yeah, I'm assuming that the losses are between 0 and 1. If they're unbounded in some direction, for this algorithm, you'd have to do something like clipping. So yeah, good question.
When you crawl data, do you crawl from public leaderboard or from private?
Both. So let's take that, like I can tell you later how we do this Kaggle stuff. It gets a little bit messy, so let's take that in the questions afterwards. But it's a good question. All right. So what about collaboration? I've talked about competition and how the competition between data scientists leads to sort of greater longevity in benchmarks, which I found surprising when I first noticed. What about collaboration, right? We're not just all about competing, right? We also like to collaborate. You know, it's like, you know, I'm looking at Jamie because such a good collaborator. So, you know, actually we've never collaborated. I don't know, but I assume you are. And oh, yes, that's right. Oh, okay. Maybe this is a bad example then. Okay, so for those of you who like to collaborate, you know, here's another thing that's going on. So as a community, we have shared priors, we have shared practices, we try out similar things, right? We don't just start like somewhere in the universe and start doing machine learning. We start from some available GitHub repository and like things that have already been done. And this leads to the fact that we all try out models that are pretty similar probably to things that other people have already tried out. Okay, and so we you know, explored this idea of model similarity a little bit. This is a paper with Mania, Miller, Recht, and Schmidt, where we found that empirically, many of the ImageNet models that we have, or in fact all of the representative ones, have very high similarity levels beyond what their accuracy levels would suggest. And by similarity, I just mean agreement in their predictions, just how many predictions are identical, okay? So just agreement in their predictions, no fancy like similarity between the parameters, just how many of the predictions you agree on. And of course, if you both have like 100% accuracy, then you agree on everything, right? So if you're very accurate, you're also very similar. But it turns out ImageNet models, the ones that have been proposed, are way more similar than their accuracy levels suggest. And we can turn that into a better generalization bound for families of high similarity models. So we can show that if you're really querying a lot of like sort of similar or clusters of similar models, you get much better generalization bounds. So let me, instead of showing you the bound, which is pretty messy, let me give you a plot, okay? So this is the ImageNet similarity plot. The left-hand side, or the y-axis, is the similarity. The x-axis shows you model pairs. We evaluated about 50 ImageNet models, so that's 2,500 pairs roughly. And what you see in the blue line is the actual similarity of these model pairs, okay? And the median similarity is about 85%. And if they were just like randomly incorrect on a fraction of their prediction, so if the errors were randomly located, then you would get the orange line. So orange line is sort of the similarity that you would get if they made random errors, given their accuracy level. And you see there's a huge gap between the actual similarity and the independent similarity. And if we take this median similarity measure and we plug it into our generalization bound, you see that the number of models you can test with non-trivial error, this is like some like 1% error, so the number of models you can test at 1% error goes up by about an order of magnitude. Okay, so you can test many more models at the similarity levels that ImageNet gives you, compared with what a carefully optimized binomial tailbound would tell you. Does that make sense? So just model similarity boosts these generalization bounds, which is fairly intuitive, I would say. Question, Grant?
Differentiate the models being similar from just some samples being much harder to classify than others?
Yeah, I think there's generally like sort of in these models kind of like a hardcore set and an easy set, sort of like a set of things that where they actually do kind of randomly error, and a set of predictions that are correlated. And that's something interesting to explore, I think, further. Yeah, yeah. That's right. So, things like boosting and ensembling, if you have independent errors, give you a big accuracy gain, right? So in some sense, this also tells you something about how effective ensembling is for these models. Good question. Right. So let me transition from community dynamics to the mind of the analyst, which might sound a little bit vague, but I'll try to make this a more concrete thing. So bear with me. So here's a common critique of data, adaptive data analysis, right? This is literally like in the last 4 years, whenever you talk to somebody about adaptive data analysis, these were like the first two things they said. These worst case bounds are overly pessimistic, and natural data scientists aren't actually adversarial. And by the way, I looked this up, what real data scientists look like, and these guys carry battle axes, okay? So I'm not buying the story about not adversarial, right? But I think it's more complicated than that. But even if you sort of buy the story of natural data analysts aren't adversarial, what do you mean by natural, right? And we all know as theoreticians just how hard it is to take a universal quantifier and relax that, right? Like sort of adversarial is like an insult for the universal quantifier, right? It's just a for all quantifier, and it's hard to relax that into a meaningful notion of benign or natural. But anyway, because this has been kind of a persistent complaint, we tried to do that. This is work with Tiana Zernich from UC Berkeley. And what we do is we model the analyst as a dynamical system that generates queries or generates models given the transcript. So given previously revealed information about the holdout set, the data analyst sort of cranks its internal system and spits out a new query. Okay, so slightly more formally, there is a hidden state H sub t. There's a state transition map psi. This is just your standard, discrete time dynamical system. And the state transition map takes in the previous hidden state and the feedback that you got in the last step. Okay, whatever that is. For example, the empirical risk of your last model. So you take in the last hidden state and the last feedback, and you spit out a new hidden state. And based on that hidden state, you put forward a new question, a new query to the test set. Okay, so queries and answers are sort of now evolving according to this dynamical system. And the interesting thing that this gives you is that you can now constrain the analyst in natural ways by constraining this dynamical system using control theoretic terms. Okay, so in particular, there's a notion of a progressive analyst, which corresponds to stable dynamical systems. And another way to think about it is that progressive analysts have kind of a recency bias. So they weight recent information more strongly and they kind of mostly work off of what was recently revealed. And there's a complementary notion called the conservative analyst, you might have guessed, which corresponds to some sort of natural Lipschitz condition on the state transition maps, you can think of it as an anchoring bias, which means that, is that 20 minutes against the hour or against the 50-minute mark? Okay, perfect, great. Just checking. All right, we're right on time, that's good. And so the conservative analysts correspond to kind of an anchoring bias, meaning that you weight initial information more strongly, and the initial information kind of anchors your trajectory, and you mostly work off of initially revealed information. So no political biases intended here, okay? And what you get is now really interesting trade-offs, okay? So you can now look at the estimation error between the best non-adaptive bound, the Rudlock-Hare-Van, and let's say the basic adaptive bound, and you will see that progressive analysts fall somewhere on the spectrum. And moreover, you can turn this knob of the stability parameter. There's a quantitative parameter that lets you sort of dial all the way from like non-adaptive to adaptive, and gives you like a rich spectrum of analysts that are neither worst case nor non-adaptive. Okay, so basically, if the system is stable, you're generally pretty close to the non-adaptive bound. If it's unstable, you're pretty close to the adaptive bound. Okay, great. You can do the same with Lipschitz. Here, the interesting thing is that you get the fancy adaptive bound, the k to the 1/4 of root n, or you can get that with noise addition. So you can interpolate between the best known adaptive bounds and the best known non-adaptive bounds with this Lipschitz parameter, so that's a little bit stronger if you want. I was like looking for the opposite of Lipschitz. I couldn't find it, so I called this dipschitz, but I don't think this is going to catch on. So I'll just I'll go over it. Anyway, so there's also if you don't buy the story about cognitive biases, there's a little bit of a different way to look at it, which is that natural analysts capture natural optimization methods. Okay, so you can show that progressive analysts, for instance, capture Bellman iteration or value iteration for Markov decision processes, and conservative analysts correspond to gradient descent with decaying step size. Okay, so it's sort of reassuring that these things that kind of seem intuitive also correspond to well-established optimization procedures and give you a new characterization of why, let's say, gradient descent with decaying step size doesn't overfit much, even though it's an adaptive algorithm, if you want, right? Gradient descent is adaptive, but this is another way of proving that it doesn't overfit much. Okay, so there are a bunch of good open problems here. Can we get the fancy adaptive bound for stability, not just for Lipschitz? How far can we relax these stability and Lipschitz conditions? We put like very strong conditions forward. There are probably weaker conditions that also work. Are there other natural properties in this control theoretic framework? And one thing I find particularly interesting is kind of to explore this connection between generalization and control theoretic stability. I think there's something to it that we should understand better. So let me finally talk about problem artifacts, which also have an influence on how long your data set lives. And let me start with a little bit of an anecdote or a story, okay? And again, I'm going back to 2015. It was really my favorite year. So in 2015, there were all sorts of headlines along the lines of computers are now better than humans at recognizing and sorting images, okay? By sorting, they mean classifying, okay? So this was a headline from The Guardian from May 2015, okay? And it referred to that the ImageNet models in absolute terms had superseded what was considered the human baseline. And the human baseline was just Andrej Karpathy, who had like labeled as a Stanford grad student a bunch of images. And it provided valuable human baselines. But nevertheless, this was never a particularly rigorous comparison. But people ran with it anyway, and it caught people's imagination. And so people have pointed out that this was kind of a sloppy comparison. I want to point out that this is actually inherently a brittle claim to make. Okay, and so there's, if you look carefully at this paper that I already mentioned by Rektorov, Schmidt, and Shankar, they show you that when they recreated this data set, they found that natural changes in the data generating process can make models perform much worse in absolute numbers without changing human performance. Okay, so you can sort of turn a seemingly innocuous knob in this data generating process that has something to do with how many mechanical Turkers select the image, and you get basically much worse absolute numbers for the computer models without changing the difficulty for humans. Okay, so this claim doesn't make any sense. It's not like these numbers are not meant to be understood in absolute terms. They have to be understood in relative terms. okay? And so this is an example of what I call a problem artifact. This is something we often overlook, but it influences how we interpret things and how we think about these problems. And ImageNet is full of problem artifacts. Here's my favorite one. If you actually look at these 1,000 classes in ImageNet, okay, ImageNet has 1,000 classes, you probably knew that. If you look at them, there are 29 Terria variants, okay? I didn't even know there was more than one Terria, but apparently there's a soft-coated Wheaton Terria, a Dendy Dinmont Terria. I'm not making this up. These are all like actual Terrias. How many, so do you know any of these Terrias? You do, you're a Terria fan, okay. So we have some Terria connoisseurs in the audience who know many of these Terria variants. I didn't know, I mean, maybe the beats me. The toy terrier? Is that a thing? Okay, anyway. Scotch terrier. I think I knew a Scotch terrier. Anyway, so the point is, this is actually pretty hard to distinguish for humans, right? Like, unless you really care about terriers, I can't distinguish any of these, right? And so many of these are actually, there's real uncertainty here for humans in like how, what terrier you're looking at, right? And, how to classify this, okay? And so what we showed in a recent paper with Vitaly Feldman, who's there, and Roy Frostig, is that some of these problem artifacts can actually help you. Okay, so in particular, the number of classes, if you actually have a lot of classes that are hard to distinguish, it can help you with mitigating data overuse. Okay, so roughly, and this is an inaccurate statement, but what we show is that for problems with M classes, in ImageNet this is 1,000, we can roughly replace the dependence on n in all of these bounds by n times m, by up to. I say as much as because priors matter, okay? You can't just like throw redundant classes in your model like, an extra class of just black squares or something like that and hope that this will somehow help, right? So priors do matter, but if you don't have a strong prior over which way these classes go, there's real uncertainty, you get as much as like a factor m in effective sample size, just from the number of classes. Okay, so let me talk about the maximum error for prior-free multiclass problems, and basically how large a bias we can create with k queries on a data set of size n and m classes. And we prove an upper bound on the bias that you can create of root k log n over m times n. So this is where you see that you do pay this factor m or there's this factor m in the denominator, which means that the bias you can create gets much smaller by a factor m. And this is like an upper bound on what any sequence of k queries can achieve. Okay, so this is an upper bound on that. We also have a lower bound, and a lower bound here kind of is an attack. So that's actually a sequence of k queries that you can implement against a leaderboard or against a data set to create a large bias. And the thing that we get for the attack is a little bit weaker. It's root k over m squared times n, so there's off by a factor m. But good thing, there's the COLT community. So this is like a COLT open problem that Vitaly is going to talk about this afternoon more, so I'm going to touch on this briefly. And all of this is in the regime where k is relatively small. So it's asking how quickly can you get off the ground with a relatively small number of queries. Okay, there's a different regime for when the number of queries is large and where we have tight answers. Okay, so let me wrap up, and how much time? I'm really ahead of time, so we can ask questions. Let me wrap up. Okay, so what did I talk about? So the summary is roughly that there have been these recent meta-analyses which reveal that adaptivity was more benign than worst-case bounds suggested. And moreover, we now have a bunch of theoretical results that in some sense could have predicted this outcome more accurately, or could have described why this is happening. And finally, the main point I was trying to make is that this theory involves, in some sense, postulates that are sociotechnical in nature, right? Statements about how the community operates, what the community values, what goes on in the mind of the analyst, and like looking closer at these different problem artifacts. Okay, so this is often where we don't expect sort of overfitting to occur or overfitting to be decided at this level, right? And there are two ways of looking at it. I want to kind of know from you later on which one you more closely identify, but they're generally like two ways of looking at it. One of them is, oh, this is great. This is really excellent news. What you talked about is wonderful news. Machine learning benchmarks have this amazing robustness and longevity, and you can use 2 decades of MNIST and a century of ImageNet, and this is great, okay? So that's sort of the positive takeaway. But there's actually sort of maybe like a more concerning takeaway, which is that if there is scientific harm to benchmark reuse, if there's something lost in our scientific practices by reusing these data sets excessively, then this paradigm of like looking at the generalization error doesn't reveal it. It doesn't measure it. It sort of flies past it. And whatever harm there is not quantifiable by this methodology. So in more operational terms, by which actionable criterion should we currently retire a benchmark, right? If you currently had to decide as a community, it's enough with this ImageNet, you know, by which criterion would we do this, right? So in some sense, it would have been better if these meta-analyses had like a bad outcome or had like a sort of the outcome that we overfit a lot, because then we could say, hey, you know, we should create new data sets, okay, it's enough with this, right? But we don't yet have this actionable criterion by which we can retire benchmarks, and I think that's a bit of a problem. Generally, I want to sort of propose a broader perspective going forward on the value of data and what we do with data. And this perspective focuses on, you know, community dynamics, the mind of the analysts, problem and data, and model and algorithm. And, you know, I ordered in this particular way from sort of what I think is the broadest category to the narrowest category. And as a community, I think we've mostly focused on model and algorithm aspects. So, you know, what properties of the model class, the algorithm, the optimizer, the regularizer have what kind of effects. And that's an important study. There is a lot of exciting stuff going on there, a lot of important things. But I don't want us to kind of forget about how important these other facets are and how much of an influence they can actually have on the things that we do, okay? So the central question that I think we should keep in mind is, what determines the health and validity of our collective scientific and epistemic activities, and not just, you know, what, do we overfit or not in like a particular, you know, quantifiable way, okay? So with that, I think that's all I had to say. Thank you very much, and I'll take your questions. Yeah, so this is a good question. The question is basically, aren't the dynamics, let's say, in industry very different from the scientific community? And it could be. My personal experience in industry is that it's actually been very similar, and that often what, you know, teams do who improve products is they set aside some test set, and they have internal, like they do internally what we do externally. So they internally try to improve on that, and every 3 months they update their model, they update their production model based on the best thing they've seen on their internal benchmark. So that's one thing I've seen a lot. But it's certainly true that there could be settings where the dynamics are different, and that would be interesting to explore. I don't know who was next. Maybe John. How about?
So one of the ways that things could differ is through online. I said you always need to do examples. You know, holdout sets are always sort of growing subsets. And then
Right.
a lot of the concerns about holdouts go away.
Yeah, so the question is, do a lot of the concerns go away in an online setting? And I think in some sense they do, and in some sense they get worse, right? So one thing you have in like things like recommendations and advertising are pretty terrible feedback loops that you're training a lot on the data that was generated by what people clicked on, which depends on what you showed them. So yes, in some sense, you have more data, but it's also algorithmically confounded. And in some sense, it's not even clear, you know, then you have different questions to answer, which I think are very interesting. And I agree with you that they don't necessarily fall into this static data set paradigm. I don't think of them as sort of solved issues. I think of them as pretty difficult problems that sort of people are still working on in these settings. But maybe you're a step ahead, so I don't know. You have some answers, yeah, good, that's good to hear. Great.
Just a thought on how industry could be different than what the rest of the research community does. Industry, maybe sometimes it's more important to actually know how well you're doing
I agree with that comment. Yeah. Nati.
Somewhat related to that, you had an amazing linear fit between the test error estimation, measuring the test error between certain samples. But there was still a significant gap there.
Right. So, yeah. So Nati's asking about the drop on that plot, and I figured somebody would. The drop, is what people would attribute to, I don't know, domain drift, right? Or like, the fact that there's some systematic difference between the new test set and the old one, right? But, so in some sense, to me, the drop is less concerning because you still, if you make progress on the old one, you make progress on the new one, right? So if it were, okay, it could be systematic overfitting, but in that case, it would uniformly apply to all models at the same, roughly the same level, right? Right, but the thing is, it doesn't, if adaptivity were the concern, the models that adapted more should show more overfitting. And in particular, what you see on CIFAR is that the drop for the newer models is much less than the drop for older models. The newer models will drop by like 3-4%. The older models will drop by 20%. So it's actually the slope goes, that way. Okay, there's a question back there. That's right. Yeah, so I guess I think about it in terms of these attacks. How would you create a bias as large as possible with a certain number of queries? And in the binary case, there is a pretty natural strategy that relies on sort of taking a bunch of random queries and like taking the ones that had a positive bias against the holdout set and ensembling them. And the problem with multiclass is that random guessing gives you much less of an advantage, because your chance of getting it right is not a half, but 1/m. So in some sense, this idea of like majority voting over these things doesn't work nearly as well. And so in some sense, it's harder to get off the ground when you have like a uniform prior. Like you don't know anything about the data set. You don't have a classifier that's better than 1/m accuracy, right? That's right, yeah. I mean, or well, in the sense like the best classifier has accuracy 1/m. So in the beginning, you don't know anything better than random guessing. That's what I mean.
I'm not sure if it's the same issue, but there's these claims in science more broadly that like scientific results not holding to reproduction and interpretation. Is that related?
Yeah, so this is a very good question. How is that related to sort of the scientific crisis, as it's often called in the empirical sciences? And this was sort of the motivation for this reusable holdout stuff, right? And we the adaptive data analysis things that we did 3-4 years ago, where we did think, that's related strongly to that, right? That people somehow, tailor their analyses to the data set until they find what they want to find, right? So that is definitely related. It's in machine learning when you are more in this like kind of benchmark competition style. I think this is the effects of that are greatly alleviated. And I would actually say that in sort of a sort of more scientific setting maybe, where you're not just like in this benchmark format, but you're actually like, you're the one in some sense deciding what statement you're going to make about what data set and what variables you include and so on. In some sense, you have more degrees of freedom, and I think that's still an area where expect adaptivity to cause a lot of problems. So that's a good question. Vitaly.
Follow up from a comment on Nagi's question. So if you think of benchmark as kind of serving two purposes. One is actually being able to compare the models, which we see that they are doing very well, and the other is providing us accurate estimates of what one could expect as a performance. And I'm sort of thinking of those as really different in these. I don't find it surprising that there could be a very large gap. Well, you observe the relative ranking, and this is exactly what one sees when we just look at the train versus test set. We know that those usually improve better together, and the gap narrows as you get closer to the zero error, because at the end, basically in most cases, you have to narrow that gap if you improve both. But we don't think of training error as being a sort of good estimate.
Sure.
Error.
Yeah. No,
In my view,
Sure.
these are very, very similar phenomena where you
Right.
you are creating some, in some sense, you are creating bias.
Right.
through Maybe various mechanisms, some things like, but that's part of it is adaptive,
Right.
maybe other things.
Yeah.
But the ranking is preserved is completely kind of, it doesn't contradict
No, I'm not saying it contradicts anything. I also, maybe one thing that related to your question is, one thing that these theoretical results don't get at is, in some sense, one-sided error. That, they always, upper bound the generalization error in like absolute terms, but they don't allow they don't allow you for this situation where you keep improving, even though the gap kind of widens, right? Let's say the two things are going apart. Like in some sense, these theorems don't say anything about model ranking, right? They say something about the absolute generalization error, and they don't, the theoretical results we have don't actually talk about this monotonicity, right? So it would actually be really interesting, in my opinion, to have theoretical results that directly say something about monotonicity as opposed to bounding the generalization error as a proxy for that. So, and I think we agree in some sense, yeah. Cool. One more question back there. Yeah. Yeah, I'm not sure I follow that addition. So the question was maybe the difference to science is that the effect sizes are smaller in science and they're larger here. I think some of the improvements are pretty marginal, right? And the analysis still applies for things like MNIST, right? We're talking about going from. Yeah, and let's chat more about it. I want to learn more about your intuition. More questions? All right. Thanks so much.